We're going to go over the code used to build the graph network and the GNNs to predict on NBA data. Project library is here, pretty straightforward, easy to install. A machine will be able to get up and running fairly quickly to use this code and replicate it. The CSV file was downloaded from a public Kaggle website. Once that was downloaded, we just loaded it into a pandas data frame, and we wanted to remove anything that was an object because when we feed this into the graph networks and for evaluations of the features, we want to just work with numeric data. So we have a good amount of data, 14,000 rows. A lot was trimmed because there was unnecessary information. The lines, or each line, each row you see here, actually is unique, but there was duplication of a lot of the data rows, and we had a function here to drop the duplicates to clean up the data. So the first thing we wanted to do to find the right features, we set up a PCA. We set a threshold of 95%, and we see 17 components explained 95% of the variance and variability, explainability in the data. So this gave us a sense that there was a lot of redundancy. The next thing we did was we used variable inflation factor to help find what were the good features. We just set a real simple linear regression just so we can run the code to get the variable inflation factor, the VIF, and that gave us 44 features, setting a threshold of 30. This was a pretty high threshold just because there were a lot of features that were above 5 or 10, so we bumped it up pretty high and still saw 44. So we wanted to then find the correlation of all this, and if we put the entire data frame into a correlation matrix, it would just be too large to see. So we broke it up into chunks, and we could immediately see some high correlation values as we stepped through. We went through 15 features at a time. So we saw a lot of features that really kind of didn't need to be part of the equation to build the graph networks. So we took the VIF, those 44 features, and again we ran it through another correlation matrix, and at this point we were able to really determine which features had very, very high similarity. So this is the field goal percentage and EFG's, I think, efficient field goal percentage, and it's pretty much measuring the same thing, so that's why we see a high value there. We see some other high values. So what we did was we reduced the features based on what we saw here to a list of these final features. And kind of have a process of reduction. We settled on these 8 features that pretty close to zero correlation with each other. From there, we wanted to prepare the data for the graph networks. So we created a couple tables. One was just with the teams and the result, and the others had just the numeric values, and these numeric values is what we would use to compute the edge weights. So here's the entire table, and then here's the table with just numeric values, and then we have the teams here, and then we have the labels that we'll use for training and for evaluation. So we calculate the edge weights. What we do is we look at the team and we look at the game ID. We go back to the previous games and get a mean of all those features for each team, and that's what we will use for the edge weights when we build the network. The reason we want to go back for the game ID because it doesn't make sense to find out what a team did 3 years in the future. That's not going to correlate to what a team is going to currently be doing. So that's why we set up the graphs in this way. We're building, we're building the graphs, and we have a multi-graph for a train and for a test graph network. So here we're just showing the graph network. We're not showing the edges because there would be a lot of them, but just showing that we were able to reduce the teams that were nominal, and we change it to a numeric value for the edges. And we just have a very simple GNN model with 2 layers and a forward feed model. So we created our train and test graph based on what we created before. We're defining the model here, and we are using 1000 epochs. And here we have the gradient. We receive the out, which are the predictions, and then we are using binary cross entropy for the loss function. And after we're training the model, then we're running a prediction on the test data, and we see that the data is, we see the results are static. So this was an indication maybe that we need to shuffle the data. That kind of gave us an idea. And we also wanted to change the GNN architecture because maybe it was just stuck producing the same weights for the nodes. So here we tried logit loss, which would be more of a probability for win or loss, 0 or 1 for what we predicted. And we had problems with this model because the tensors did not match up the way that it should. It kept on pulling the teams where it should have been pulling the games. So this 11,000 indicates the amount of games in the train data set, and this indicates the amount of teams. And we should get game to game, but this model just was not looking at the right part of the graph. So we did some research on self loops and wanted to add that into our GNN. So we pretty much set it up the same way, using the same features, using a multi-graph, adding the nodes for encoded values for the teams, and the GNN layer had some self loops that were added to it that was different from a GNN layer before, and this gave us a different error, but still it had a hard time reconciling teams and the games, the edges. We really wanted the model to train on the edges and not focus on the teams so much, but we still got a conflict with the tensors that were fed in and what was created from the model. And so of all the examples that we've seen in class, the MooTag example that used an Atom frame database looked to be the closest match. It's from lecture 7. So we looked up how we could create our data to mimic the MooTag dataset. And there is a custom dataset library or class that could read each one of these different files and produce a graph network. So what we did was we're creating a data set, and then that data set is put into this class that would mirror what the MooTag data set had. The reason we put this in a loop is because we wanted to create different graphs. And we were hoping that that would train the GNN better to make better predictions. It wasn't seeing the same thing over and over again, where it would make the same predictions, where we'd see static loss and accuracy values as before. So we're just creating a list of this custom data set, and by setting the index of 0, it means that we're pulling the graph from the custom data set, which is part of the object. And then the test data set, we could just have one of them. We didn't need that to alternate. What was most important is that we were alternating the train data set. So we were able to see for one of the data sets that were created, we had 2,000 nodes and edges, which represent the games. And then we're using a graph convolution network with 3 layers. We just had to change some of the features that were different in class to fit the number of output and the number of input. Number of input is the features that would represent the edges, and we just have a binary win-loss outcome. The first problem we saw here, though, is that when we loaded the train data set into the data loader, it only found one data object in there. These are the 5 graphs that are created, but we really wanted to emulate the MooTag data set, that we had different data sets or different data objects in the train loader with different number of graphs. So we weren't able to replicate that, and we figured that was going to be a problem. It turned out to be a problem because as we trained it, we see that the accuracy and the losses, well, pretty much the train and the test accuracy fluctuate a little bit. That's just because of the different graph networks that are in there, but it's still close to 50%. So flip a coin, did a team win or lose? This model is pretty much doing the same thing. You would think it's better than 50-50% because if you have a dominant team playing a weaker team, the odds are pretty strong that that stronger team is going to win. And the model just wasn't able to assign any of those weights to make an informed decision on that. We did a sigmoid on the output. Even though it was binary cross entropy, we still saw what may have been confidence or probability values associated with the output that the GNN created, or GCN in this point, created. So we just did a sigmoid on it to force it to 0 and 1. That at least allowed us to have an apples to apples comparison for this project. So a lot of work to be done. Kind of disappointing that I wasn't able to fit the model the way that it should. It was an exciting project. Definitely no problems with the data. Issues stemmed with creating the graph network and then feeding it into the GCN and having the right shape of the data coming out of it. So it was fun. I learned a lot, but unfortunately I just didn't have the results to make this a very exciting, worthwhile project to pass on to others.